Hi, good afternoon, everybody. My name is Erez Cohen. I'm with Mellanox, and I will be talking about virtual switches. I'll let the guys come in. Maybe we'll start. I don't think we have a lot of time. So Livna talked about a very large kind of, can you guys hear me? Okay, I don't hear myself. Okay. So Livna talked about the system-wide solutions for telco, and I'm going to focus on a very specific element. There will be a tie-in to OpenStack, obviously, because we are in an OpenStack day, but we'll focus specifically about virtual switches. So first, what are virtual switches? Virtual switches are the element inside the host, inside the servers that provide connectivity between the virtual VM, the VM or container for that matters in many cases. Virtual switches are being used also for containers. They started as very basic switching capabilities, but later they're now adding much more than just switching. They also provide routing and many other capabilities. The most common and most popular virtual switch today in the industry is OVS, Open vSwitch. This is a project that was contributed into Linux by Nicira that was later on acquired by VMware. And it is a very advanced virtual switch. It has flow-based switching, not only FTP-based. So basically, we can look at every packet, classify it into a flow, and then do different actions. If you are familiar with OpenFlow, it's a very similar concept. It's actually using OpenFlow in many cases. Virtual switches are a critical element in clouds. Basically, in many cases, they are implementing the SDN layer, the software-defined network. The software-defined network controller typically configure the virtual switch to implement the different virtual networks that we would like to deploy. So those are virtual switches, sorry, and they're very good, but they have some challenges. And the challenges are mostly around performance. Virtual switches are network elements. In essence, they are doing networking, and they're running on the main server, the main CPU. And CPUs are not, general purpose CPUs are not network elements, we're not supposed to be network elements. Thank you. And when we are looking at, now I think it's a little bit too loud, at least to me. Are you guys okay? Only me hear it? Okay. So virtual switches, when we look at high performance workloads like VNF, telco workload and so on, we need a lot of performance, and virtual switches don't do that very well. Mostly around message per second, when the CPU needs to look at every single packet, it just don't keep up. Latency, the jitter, the ability to be consistent on the performance is very limited. The operating system is not real-time, so we cannot guarantee actual timing for the packets. And obviously, the virtual switch consumes a lot of CPU because it's working on every packet. So overall, it provides us a very slow, unpredictable, and inefficient networking solution, but it works. So functionality is there, doesn't really work very well. Those problems are typically seen when we need a lot of performance. And this is really in the telco and scientific workloads. You'll see that OVS or virtual switches in general just doesn't pick up. The solution that we are offering, or we are seeing the industry offering, actually it's not only Mellanox, is accelerating virtual switches by hardware. And if you look at virtual switches done in software, and this is kind of this picture over here, they get the work done. And they will move the packet from one side to another, but not very efficiently. And what we want to have is we want to enjoy both the flexibility that virtual switching and SDN provides. We don't want to throw that away. But just like in our data center, the switch and the routers will be run on dedicated hardware, we do want to have hardware that will do the data path elements, will work per packet and will do it very quickly. So we think that the combination of software and hardware is the right way to get the data moved properly. Actually, when you do this combination, we can cut the amount of servers that we need to implement network services, in some cases by up to 100 times, which is very significant. If you think about a core network that needs to have 100 times more servers to implement the same capability, that's obviously not viable. It will not be able to sustain the cost and the space that is required. So hardware acceleration is definitely a must. When we go and look about how do we do hardware acceleration, there's multiple ways to do that, but in any case, you're touching a lot of elements. You need to look at the different hardware architecture that vendors like Mellanox and others in the industry has. There is different operating system support that needs to happen, orchestration for the cloud, and the application level itself may need to support that. So there's quite a lot of things that we need to look at, and when we look at the architecture, there's also two ways to do that. One way is the top-down approach. And this approach was tried multiple times. The concept here is to define general concept of acceleration, and even not only for network, but general acceleration. Look at acceleration as an object and then build a framework around it to manage it and to deploy it and to control it. There were several attempts to do that. None of them succeeded through OPNAV and other consortiums. And the reason is that it's very complicated to do it top-down, because you need to look at too many things from above. As I said, there's a lot of layers that needs to be addressed, and the interfaces between them is quite complicated. The other direction is the bottom-up approach. And this is what Mellanox did, and I'll present that in a minute, around accelerating OVS. The bottom-up approach means that we start with generic hardware elements. Obviously, Mellanox and Intel and Broadcom and all the other vendors out there will not have the same hardware. That's obviously not acceptable and not logical to expect. But at the same time, we do expect that the elements will be modeled in a way that can be used through standard APIs that will be generalized. The next thing is to define an API in open source consortiums rather than kind of specification to consume those acceleration, like the Linux open source project or OpenStack itself, and then integrating into upper layers as we go up. And it depends how up we want to go, and I'll describe two use cases in a minute. This approach that we took is starting to formalize into kind of the standard approach in the industry, and I'll describe that. So the acceleration, the hardware acceleration is not only for networking, but the examples that we'll do here is OVS specifically, virtual switch. This can apply to many other solutions or application that can be network application or not network application. So what have Mellanox did? What we have done is basically we looked at data path behavior, especially with flow-based aware data path. And what we see is that the steps are kind of repeating themselves. So there's, for every packet that goes in, there's some kind of a classification process. So we need to look at the packet and decide what packet is it, who sent it, who is receiving it, what flow does it belong to. And then once we know, we do some action. The action can be encapsulation, decapsulation, can be forward, can be modify, can be route, can be multiple things. And then this process can repeat itself multiple times until the packet is sent out. This is standard pipeline, data pipeline that is very similar to OpenFlow and other approaches. And what we have done is we accelerated this pipeline while we're not touching the control plane. So we are leaving the control plane to the software, to the SDN. We leave it in the software domain. But what we want to do is all the heavy lifting that needs to do on every packet, kind of the dumb things, but the dumb things that slow everything down, we want to accelerate to have it much faster. So in our hardware, in our network adapters that you can see in our booth outside, inside the adapter we have a switch. We're talking about vSwitches, virtual switches. In our adapter we have an eSwitch, embedded switch. It's real switch. It's not implemented in software. It's not implemented in a CPU. It's real physical ASIC, silicon, that implements a very advanced flow-based switch. And as you can see here in this kind of diagram, this is only the embedded switch, the eSwitch implementation within the NIC. Of course, other than that, there's a lot of other elements inside the NIC. There is, all the Ethernet elements and the forwarding and RDMA and all the other things that we have. But specifically the eSwitch, what it does, it has classification mechanism. So it has hardware engines that do classification in hardware. So it's very, very fast and it's very flexible. And for every classification, it can have multiple tables of actions, and the action can be very wide. It can steer the packet, send it to some port. It can drop it. It can encapsulate it into VXLAN or MPLS or whatever tunneling technology that you can think of. It can monitor and so on. So very similar to what OVS does in essence. The nice thing is that all this element is done in a very efficient hardware, but at the same time very scalable hardware. So we can scale these tables to many hundreds of thousands and millions of flows. We're not limited because of it is in silicon. We can scale very, very widely. This technology is called ASAP Square, accelerated switching and packet processing. And this is the basics. This is kind of the hardware building blocks that with them we can accelerate multiple things, including OVS. So before we talk about OVS acceleration specifically, let me just say one word about SRIOV, because it will be important for our discussion. SRIOV stands for Single Root I/O Virtualization. This is a PCI specification, started in, 2007, I think, or 6, which basically provide another way to do virtualization in servers. In what I showed earlier is this picture. This is what we call para-virtualized, where the virtual machine is connected to the hypervisor through software, goes into an embedded switch, and then serializing everything to the NIC. SRIOV, which, by the way, is not only for networking, it's a general concept on PCI, but specifically I'll explain that over on network device. SRIOV provide a way to present the hardware, in our case a NIC, to the VM directly rather than through the hypervisor. So basically the virtual machine see physical NIC, kind of a portion of the NIC, but for the virtual machine, it looks like a real NIC. It provides a direct access between the VM to the NIC and back. So basically bypassing the hypervisor altogether, and by that provide very high performance. There's additional benefits for SRIOV. I'll skip them, but if you guys want, I can talk about it more later. So with the ASAP Square Direct, the accelerated switching and packet processing capabilities in SRIOV, we can provide very interesting integration and acceleration into OVS. And here, I'll stay a little bit with this slide and I'll explain it. Here you can see some of the concept, the architectures that we have implemented and we are driving through the various open source organization. The first is OVS offload. In this mode, what we are doing is we're connecting the virtual machine to the NIC directly with SRIOV. Now this, as I said, been present for a long time, probably over now 10 years, and we have integrated SRIOV into OpenStack, so you could use, and you can still use SRIOV with OpenStack. So what's new here, basically, right? So I can use a SRIOV today with OpenStack. I don't need ASAP Square. The main difference is that when you use SRIOV without ASAP Square, without OVS offload, you bypass completely the hypervisor. So if you have an SDN controller, if you have, I don't know, Open Daylight or whatever SDN controller, Nuage running on somewhere in the cloud and controlling your OVS, the OVS is unaware of this virtual machine because they are SRV, they are bypassing the kernel altogether. And by using SRV, you gain a lot of performance, but you kind of lose the whole SDN concept. What we have done here is we connected the two. So we provided SRV connectivity, but at the same time, we make OVS aware of those ports through some new capabilities in Linux called representer ports. And then we offload the flows that are relevant for those VMs to the embedded switch. So now traffic that will go from the wire into the VM and out will be enforced by the same rules that OVS defined. So the control plane is still with OVS, the data plane is done in hardware. And the improvement in performance is significant. I'll show you some numbers in a minute. So this is what we call the full offload or ASAP Square Direct. This is where we completely move the data path from software to hardware. Of course, there is some fallback mechanism where when the embedded switch doesn't have the rule, it will throw it to OVS and then it can still send it directly. But in general, we offload all the flows from software to hardware. This is one use case. This is the full offload. The second use case is OVS acceleration. In this case, as you can see, the virtual machines are still connected with para-virtualized interface to the hypervisor. So the VM itself is unmodified altogether. And what happened here is that OVS split the work of packet handling between the main CPU and the hardware, the NIC hardware. So if you remember, I showed in this diagram here that the data path will typically look like a pipeline of multiple stages, that there will be multiple things. For example, it can be encapsulation and then forwarding and then, I don't know, something else. Mirroring, you know. So what we're doing here is we're taking some of the data plane and place it in with the embedded switch. The best example for that is classification. For every packet that arrives into the virtual switch needs to do classification. It needs to look at different fields of the packet and decide what flow ID is this packet belongs to. It takes about 30 to 40 CPU cycles per packet from your main CPU per packet. That's a lot, especially if you're going through, you know, high-speed networking, not slow. What we can do is we can have OVS program this embedded switch to do the classification for it. So the embedded switch will do the classification and provide some kind of cookie or some kind of idea into the packet so that when OVS get this packet, it just needs to look at this integer instead of looking and doing the full classification. That's one way to accelerate. Another thing that we can do is do the encapsulation, decapsulation into VXLAN or other virtual tunnels and so on. So with that, we don't completely bypass the hypervisor. The performance will be smaller, but at the same time, we maintain kind of a little bit more backward compatibility compared to this mode. So this has much more performance gain. This has much more backward compatibility. This is two cases where we accelerate the virtual switch, the infrastructure of the hypervisor. But there's more into ASAP Square than this. This, for example, a case where we accelerate the application itself. So let me explain how does it work. So basically, if you think about NFV is all about network function virtualization. So the applications here are typically network application, routers, firewalls, load balancers, VCPE, you know, all those kind of applications that are network application in essence. And all those applications also have the need to do classification, to do encapsulation, to do DDoS prevention, and a lot of elements that this embedded switch can help. And if you think about, let's say, I don't know, you name it, load balancer. So packet will go in, they will need to do classification and then decide where to send them, and it will send it out. for load balancer, we can do this classification in this embedded switch and provide the packet already classified, just like we did for the OVS in the other use case. This is one way that we can accelerate. Another way, and this is a little bit more advanced, is that this application can program the embedded switch with what to do with every packet. So if this packet belongs to this flow, send it over here. So a load balancer maybe look like a control plane that configures the hardware, and then every packet that goes in will do all the work and then sent out even without going to the application itself. This is kind of a more advanced use case. We call it hairpin mode because the packet will go in and out directly. Yes? Excellent question. So the question was, when we accelerate OVS, then there's a single entity, so it's easy to kind of reflect those rules. How can I accelerate application when there may be multiple of them, maybe even several tens or close to hundreds, right? So I didn't explain that, but I will touch on that now. This is the embedded switch that I mentioned earlier. Actually, it has two elements. There's the embedded switch, and then there's the VNIC. And for each of them, the VNIC is kind of the port that goes to the VM. And for each of them, there's different kind of embedded switch. So we have for every VNIC switch for itself, which is the domain of that application. And all of them kind of fall into the main embedded switch. So when we talk about the OVS rules will go in here. When we talk about the application, the rules will go in here. And each of those are completely segregated and protected. Yeah, so and they can work together. So in the example I showed earlier, when we have, for example, a load balancer, the load balancer will configure this element, and the OVS may configure this element, and they will work together. There's no conflict. How much time do I have? 8 minutes. I'll try to leave about 5 minutes for questions. So this is the application acceleration I just mentioned, and I'll move forward and talk a little bit about, so how do we get all these things together? So the architecture sounds very nice. It's actually, when it puts in this way, it kind of sounds very straightforward. But in order to do that, we had to do a lot of work. And we decided as a company, Mellanox is a very kind of an open source organization. We're trying to keep everything that we can open and available for the community. We decided to take the open source approach here as well. This decision kind of was a very difficult decision, because if we would have our proprietary solution, we could have been in the market about a year earlier. We decided to go open source, and with open source, there's a lot of community work, and you need to convince everybody, which take a lot of time. So we decided that this is still the right thing to do, even though it kind of hurt us in the short term in terms of revenue generation. So we took the open source direction, and you can see the different projects that we had to work with in the community. The first and most important, I think, is the Linux kernel community. There's a lot of things that we had to improve, enhance in the Linux kernel. The representative port is new concept that was added into Linux. TC is a tool and API in Linux traffic control, which was enhanced to do hardware offloads. And we started working on that for about 3 years ago, with the community, convince them and having discussion on how it should be implemented properly. I'm happy to say that at least everything is now upstream since kernel 4.13. Really recent, but everything is upstream already and was accepted. DPDK community, one of the APIs other than TC is DPDK. DPDK community was also very supportive, and there's also a way to offload those flows through DPDK. This is also already upstream. OVS user space had to be changed in order to reflect those changes. I'm happy to say that the first patches were accepted this week, and this should happen in about 2 or 3 weeks. All those patches should be in. And lastly, and this is why we are here, OpenStack community, a lot of this has to do with how do I manage this and orchestrate this in OpenStack. And Moshe Levy, can you raise your hand, please? Moshe is the lead developer for SRIV in the community, in OpenStack community, and also driving those patches into OpenStack. So everything is in very advanced stages. And the most important thing is that it is completely hardware vendor agnostic. The easiest way for us to do would be to drive it as a Mellanox proprietary package, but we decided that we think that it needs to be open in such a way that every vendor can implement that. And if you look at the communities, you'll see that Netronomes and other already writing their kind of elements into it, and that kind of becoming the standard for hardware acceleration. All right, so it was very hard, and it was not too fast, but I think that if you look at the results, it's quite impressive. So what you're seeing here is comparison between what is kind of the highest performance alternative in the industry today, which is OVS over DPDK. DPDK is dataplane acceleration. It's a layer that provides kernel bypass, and there's a model of OVS that runs over DPDK to get faster access to the hardware. Versus OVS offload, which basically, as I said, the hypervisor reflect the rules into the embedded switch, and then the VM connect with SRIV. We compare those two. The VM themselves are the same. We are injecting packet from the packet generator all the way to the VM. The VM is doing forwarding and sending it back to the packet generator, Exia in this case, and we compare the results. The result, as you can see here, when we do few flows, we get 7.6 with DPDK, OVS DPDK, compared to 33 million. You can see it here, which is amazing. There's I don't know how many X's. It's about 4 X's or 3 X's. But even more interesting and even more important, with DPDK, you need to invest about 2 cores to get to those numbers. So 2 cores out of your server are in the garbage doing DPDK. When we do hardware acceleration, we get 0 cores because it's not CPU dependent. When we scale the numbers, the gap even grows between 2 to about 16 million. And I'm happy to say that in this week, actually just I didn't even have the chance to put those numbers. We ran our latest NIC. This is with ConnectX 4 devices. ConnectX 5, which was recently released, I have new numbers just from this week. And this number is now exactly double. So we are going from 7 or 8 million-ish to 66 million. Just to give you a ballpark number, AT&T spoke about the need for packet per second inside the VM. Their target said that they're envisioning in 2020 that they'll need, that the industry will be at about 50 million packet per second. We kind of moved 2020 to 2017, so we are very proud. Few more slides. I think I have 3 minutes. So really quick, where do we stand? I think I covered that. We are really ready to go into production in multiple ways. I think that with Red Hat and others, we're already integrating that into their next releases. So this will be available as GA very soon upstream and inbox. But OVS is not the only application that can benefit from that. There's others. One example is CloudIgo. Sagi is here. I'm sure Gal Sagi is here. I'm sure you know. CloudIgo is a company that looking very differently into network services and breaking them and making them much more efficient than how they're implemented today. They're using breaking up the services and programming the services into the right place in the network, including the NIC. And this is something that we're working together and we're very proud of. And there are others, including FDIO, which is the Cisco kind of VPP, vector packet processing, OpenControl, and many, many other applications that are all network applications that can take advantage and make VNF or the whole telco transition into VNF reality, because suddenly they need much less hardware because they have much more performance. And with that, I'll leave 1 minute or 2 minutes for questions. Yep. In OpenStack. How do you manage what? Those flows? Yeah, you're right. You're right. That's a good question. Maybe I'll explain it here. In this diagram here, you can see that this is the OVS implementation. It has a user space and a kernel module. This is the normal one, right? All the policy is done here, and the policies are programming flows into the kernel. In our case, also to the hardware. Up here, there's a policy mechanism. This policy mechanism was enhanced to also know what to program to the hardware and what not to program to the hardware. The default is offload whatever you can, but every system can choose a different policy. There was another question there. So the work that we're doing is going upstream. So from compatibility mode, once the code is upstream, then every newer code will be there. We hope that we will be with all those changes into 2.8. It is going to be closed in about a month. So if we'll make it, we'll be in 2.8. No, we can do backporting, of course, but probably we'll do that together with Reddit at some point. Any other questions? Yeah.
Okay, so environmental provision. So if I'm providing a environmental sheet to a tenant, so how do I make sure they don't just use this card to change properties?
Bare metal, there's no OVS, so I'm not sure I follow the question. So the question was, what do we do about bare metal, and how do we make sure that they don't use this capability, right? So there's no OVS, so I'm not sure.
Right, there's no OVS, but it's still the terminal, still communicating.
Let's take it. I think I'm running out of time. Yeah? Offline, yeah. We'll take it. Okay, thank you very much.